February 26, 1942. At Camp Allen, Virginia, the U.S. Navy commissioned its first Naval Construction Battalion. According to Bureau of Yards and Docks records, these 1,073 men represented a radical departure from traditional naval doctrine, combat engineers who would land with assault forces and build under fire. Within hours of formation, advance elements were boarding transports bound for the Pacific, carrying bulldozers, graders, and a mission that would rewrite the timetables of amphibious warfare. Japanese planners anticipated that captured airstrips would remain unusable for months, giving their forces time to regroup and counterattack. According to Imperial Navy assessments recovered after the war, standard engineering doctrine suggested 6 to 8 weeks minimum for establishing functional runways on Pacific islands. Within 20 days, this assumption would prove catastrophically wrong. In just 3 weeks, these Naval Construction Battalions, nicknamed Seabees, would demonstrate that American industrial methods could compress months of engineering work into days, delivering 6,000-foot runways while Japanese bombers watched helplessly from overhead. This was the moment when military engineering proved that speed equaled survival in the Pacific theater. Subscribe now and tell us in the comments if you knew about this forgotten engineering revolution that accelerated every American victory from Guadalcanal to Okinawa. The attack on Pearl Harbor exposed a fundamental weakness in American Pacific strategy. According to Joint Chiefs of Staff assessments from early 1942, the Navy possessed sufficient carrier strength for offensive operations, but lacked the land-based airfields essential for sustained campaigns across the vast Pacific theater. Traditional Army Corps of Engineers doctrine emphasized permanent construction using concrete and steel, materials that required months to transport and install across thousands of miles of ocean. Navy planners recognized that winning the Pacific demanded a new approach: rapid airfield construction using locally available materials and prefabricated components. The logistical challenges exceeded anything previously encountered in American military history. According to War Department transportation studies, each standard concrete runway required approximately 10,000 tons of cement, steel reinforcement, and aggregate materials. A single 6,000-foot concrete runway demanded 45 Liberty shiploads of construction materials, consuming shipping capacity that could alternatively deliver 180,000 gallons of aviation fuel, 12,000 tons of ammunition, or 6 months of food supplies for 15,000 frontline personnel. Navy planners calculated that permanent construction methods would limit offensive operations to 1 major airfield per quarter, a pace that would extend Pacific campaigns beyond acceptable timeframes. The transportation bottleneck proved even more severe when considering Pacific distances. According to Navy logistics assessments, concrete materials shipped from West Coast ports required 45 to 60 days transit time to forward areas, with additional delays for unloading and inland transport on islands lacking adequate port facilities. Storage requirements for concrete components demanded covered warehouses and climate control that proved impractical on tropical islands subject to monsoon conditions. Cement degradation during extended storage periods could reduce structural integrity by 30–40%, requiring expensive testing and quality control procedures that further delayed construction timelines. These factors convinced Navy planners that traditional construction methods would prove inadequate for the rapid pace of Pacific operations necessary to maintain strategic momentum against Japanese defensive preparations. Admiral Ben Moriel, chief of the Bureau of Yards and Docks, proposed combining civilian construction expertise with military organization. According to Bureau records, the first Naval Construction Battalions drew personnel from America's building trades, carpenters, electricians, heavy equipment operators, and engineers who understood industrial construction methods. Unlike traditional military units, these battalions prioritized construction capability while maintaining military organization necessary for combat operations. Navy specifications called for self-sufficient units capable of operating independently for 30 days, equipped with organic heavy machinery, portable concrete plants, and specialized tools for rapid runway construction. The organizational structure reflected this dual military-industrial character. According to training documents from Camp Peary, Virginia, each battalion contained 1,073 men, organized into 4 construction companies, a headquarters company, and specialized detachments. Construction companies included equipment operators, carpenters, steelworkers, electricians, and general construction workers with civilian experience in large-scale projects. Each company operated standardized heavy machinery sets, including bulldozers, graders, rollers, and trucks, capable of independent construction operations. This organizational approach enabled parallel construction activities across multiple work sites while maintaining flexibility for tactical requirements. The tactical doctrine emphasized speed over permanence. According to training manuals developed at Camp Peary, Seabees units would accompany assault waves, establish defensive perimeters around construction sites, and begin runway preparation within hours of landing. Standard procedures called for coral-based surfaces rather than concrete, using locally quarried material compacted to engineering specifications. Pierced steel planking, PSP, interlocking metal sections developed by the Army Corps of Engineers, would provide all-weather surfaces capable of supporting fighter aircraft and medium bombers. Equipment specifications reflected this emphasis on rapid deployment and operational flexibility under combat conditions. Each battalion received a standardized machinery complement designed through extensive testing and operational analysis. Caterpillar D7 and D8 bulldozers for clearing and grading operations, Galion road graders for fine surface preparation and drainage control, sheep's foot and smooth drum rollers for achieving specified compaction densities, and Euclid dump trucks for coral transport and material distribution. According to Bureau of Yards and Docks procurement records, specialized equipment included portable rock crushers capable of processing 200 tons of coral per day, producing specified gradations essential for structural integrity, concrete mixers for specialized applications requiring permanent construction, welding units for PSP installation and equipment repair, and electrical generators providing reliable power for construction operations and defensive lighting systems. The machinery selection process considered multiple factors beyond basic construction capability. Equipment weight limitations matched LST cargo capacity, with maximum individual machine weights not exceeding 32 tons to ensure compatibility with standard landing craft hoisting equipment. Fuel consumption rates were calculated to ensure 30-day independent operations using organic fuel supplies, while maintenance requirements emphasized simplicity and parts availability under austere conditions. Durability specifications accounted for salt spray corrosion, coral dust abrasion, and tropical humidity that exceeded normal commercial operating conditions. The entire equipment set was designed for LST transport, with machinery weights and dimensions precisely matched to landing craft capacity limitations, cargo handling equipment, and beach unloading procedures. This integration of construction capability with amphibious logistics represented a significant innovation in naval engineering doctrine that would prove decisive in subsequent Pacific operations. The first Seabees deployments to the South Pacific in mid-1942 served as operational proving grounds for rapid airfield construction techniques. According to 6th Naval Construction Battalion records, initial operations at Espiritu Santo and Ifate revealed critical gaps between training scenarios and combat realities. Coral formations varied significantly between islands, requiring different extraction and processing methods. Japanese air raids interrupted work schedules, forcing crews to develop procedures for rapid equipment dispersal and protection. Standard Army airfield specifications proved inadequate for Pacific conditions, where monsoon rains, coral dust, and salt spray created unique maintenance challenges. The geological challenges required immediate adaptation of standard construction procedures developed for temperate climates and conventional soil conditions. According to geological surveys conducted by Seabees units, coral formations ranged from soft, easily excavated material resembling coarse sand to consolidated limestone requiring controlled blasting for efficient extraction. Porosity characteristics varied significantly, with some coral types providing excellent natural drainage, while others required extensive subsurface preparation to prevent water accumulation during tropical storms. Chemical composition analysis revealed calcium carbonate content exceeding 95% in optimal formations, providing natural cementing properties when properly compacted. Soil-bearing capacity tests revealed that properly compacted coral could support aircraft loads exceeding concrete specifications, achieving bearing capacities of 8,000–12,000 pounds per square foot. But obtaining proper compaction required moisture control techniques and specialized equipment operation not covered in standard engineering manuals. The variation in coral characteristics between different Pacific islands necessitated rapid adaptation of construction procedures for each operation. According to technical reports from multiple construction battalions, coral deposits on volcanic islands typically contained basaltic inclusions that improved structural properties but required different processing methods than pure limestone formations found on atolls. Grain size distribution varied from fine coral sand, requiring stabilization additives, to coarse rubble, providing excellent drainage and compaction characteristics. Weather exposure effects proved critical, as surface coral exposed to sun and salt spray developed hardened crusts that resisted excavation, while subsurface material remained soft and workable. These discoveries led to rapid development of coral-specific construction procedures that became standard practice for subsequent operations throughout the Pacific Theater. Intelligence reports from MAGIC intercepts revealed enemy confusion regarding American construction capabilities. According to naval intelligence summaries from late 1942, Japanese commanders consistently underestimated the speed of Allied airfield development, planning counterattacks based on assumptions that captured strips would remain unusable for 6 to 8 weeks. This intelligence advantage allowed American planners to accelerate construction timelines, knowing that enemy forces lacked accurate information about Seabees capabilities. MAGIC intercepts also provided advance warning of air raids, enabling construction crews to implement protective measures and minimize equipment losses during attacks. The Guadalcanal campaign provided the most intensive early test of Seabees methods. According to 6th Naval Construction Battalion after-action reports, Henderson Field required immediate expansion and hardening to support sustained fighter operations. Japanese naval bombardments and daily air raids created a continuous cycle of damage and repair, forcing Seabees to develop rapid patching techniques using prefabricated coral and PSP sections. Construction crews worked primarily at night, using hooded lights and blackout procedures to avoid detection. Work gangs developed standardized repair procedures, crater assessment, debris removal, subgrade compaction, coral fill placement, and PSP installation, all accomplished within 6 to 8 hours of damage assessment. Training modifications implemented in late 1942 reflected lessons learned from early Pacific operations. According to revised Bureau training curricula, new battalions received enhanced instruction in coral quarrying, drainage engineering, and blackout construction procedures. Combat engineering training emphasized defensive tactics, including machine gun employment, perimeter security, and coordination with Marine and Army units during joint operations. Equipment modifications included improved lighting systems, enhanced communications gear, and specialized tools for PSP installation under combat conditions. By early 1943, Seabees construction procedures had evolved into standardized methodologies capable of delivering 6,000-foot runways within 20 days of landing. According to 24th Naval Construction Battalion records from the Russell Islands operation, the process began with reconnaissance teams accompanying assault forces to assess terrain, drainage, and material availability. Survey crews established grade lines and drainage patterns within hours of securing landing zones, using engineer levels and transit equipment to determine optimal runway alignment. Quarry teams identified coral deposits suitable for runway base material, testing compaction characteristics and establishing extraction sites. The construction sequence followed rigid timelines designed to maximize equipment efficiency. According to standardized procedures documented in Navy Construction Battalion technical manuals, bulldozer crews cleared vegetation and topsoil along 200-foot runway corridors, creating windrows of organic material for disposal. D8 dozers with root rakes proved most effective for jungle clearing, capable of processing 500 linear feet of 200-foot wide corridor per day under optimal conditions. Simultaneously, quarry operations commenced coral extraction using bulldozers, scrapers, and blasting teams when necessary. Rock crushers processed coral to specified gradations, typically 3-inch maximum size for base courses and 1-inch maximum for surface applications. Grading operations required precise elevation control to ensure proper drainage and aircraft operations that met exacting Navy specifications for fighter and medium bomber support. According to engineering specifications developed by the Bureau of Yards and Docks through extensive field testing, runways maintained 1% longitudinal grade maximum with 2% transverse crown for watershedding, tolerances that required careful survey control and skilled equipment operation under combat conditions. Elevation variations exceeding these specifications could cause aircraft control problems during critical landing and takeoff phases, particularly for heavily loaded bombers operating at maximum gross weights. Galion motor graders achieve final grade tolerances within 0.1 feet of design elevation, working in conjunction with survey teams using engineer levels for continuous verification throughout grading operations. The precision required for aircraft operations demanded sophisticated quality control procedures adapted for rapid construction timelines. Survey crews established permanent benchmarks using concrete monuments or steel stakes driven to refusal, providing reference points for elevation control throughout construction operations. Grade stakes were positioned every 50 feet along centerline and edges, with intermediate stakes added in areas where terrain changes required closer control. Cross-section measurements verified transverse crown dimensions and drainage patterns, ensuring that surface water would flow to designated collection areas rather than ponding on operational surfaces. These survey procedures, while time-consuming, proved essential for creating aircraft surfaces that met operational requirements while maintaining construction speed necessary for tactical advantages. Base course placement proceeded in carefully controlled 6-inch compacted lifts using coral material processed to engineering specifications, with each lift requiring complete compaction before placement of subsequent layers. According to compaction specifications developed through field experience, sheep's foot rollers achieve specified density through 8 to 12 passes, depending on coral characteristics and moisture content maintained during placement operations. Lift thickness control prevented segregation and ensured uniform density throughout the base course, while moisture content management using water trucks and distribution equipment maintained optimal conditions for compaction. Quality control procedures required nuclear density testing, where available, or standard Proctor compaction tests to verify engineering specifications that ensured adequate bearing capacity for sustained aircraft operations under combat loading conditions. PSP installation represented the most technically demanding phase of runway construction. According to technical specifications, standard PSP sections measured 10 feet by 15 inches, with interlocking edges designed for rapid assembly. Installation crews developed procedures for laying PSP in 50-foot sections, using specialized tools to ensure proper alignment and joint security. Each 6,000-foot runway required approximately 4,800 PSP sections, weighing 120 tons of steel matting. Installation rates averaged 800 linear feet per day, with experienced crews, requiring precise coordination between material handlers, installation teams, and quality control inspectors. Completed PSP surfaces provided all-weather capability for fighter aircraft and medium bombers, with load ratings suitable for aircraft up to 65,000 pounds gross weight. Auxiliary construction proceeded simultaneously with runway development. According to standard airfield layouts, each installation required taxiways, dispersal areas, fuel storage facilities, and operational buildings. Taxiway construction followed simplified procedures using coral base courses and PSP surfacing, typically requiring 3,000 linear feet of 50-foot wide pavement for adequate aircraft circulation. Dispersal areas consisted of coral-surfaced revetments capable of protecting individual aircraft from fragmentation damage during air raids. Fuel storage facilities used standard Navy underground tank installations with coral-covered berms for blast protection. These auxiliary facilities added approximately 5 days to total construction time, but provided essential operational capability for sustained flight operations. The continuous cycle of Japanese attacks and American repairs developed tactical innovations that proved as important as initial construction capabilities. According to Henderson Field operational reports, Japanese bombers typically attacked during dawn and dusk periods when aircraft were most vulnerable. These raids created predictable damage patterns that enabled Seabee units to develop standardized repair procedures optimized for rapid restoration of operational capability. Damage assessment teams developed expertise in evaluating crater sizes, PSP damage, and drainage disruption that enabled accurate repair time estimates. Repair operations emphasized speed over permanence, accepting temporary solutions that restored immediate operational capability. According to standard repair procedures, crater filling used readily available coral and sand materials rather than specified base course gradations, achieving adequate bearing capacity for temporary operations. PSP patch installations used simplified connection methods that provided adequate surface integrity without the precision required for new construction. These expedient methods enabled runway restoration within 4 to 6 hours of damage occurrence. Equipment positioning and protection procedures developed through combat experience maximized repair capability while minimizing losses during enemy attacks. According to operational procedures, critical equipment including bulldozers, graders, and compactors were dispersed in prepared revetments that provided protection against fragmentation while enabling rapid deployment for repair operations. Fuel supplies, spare parts, and repair materials were cached in multiple locations to prevent single attacks from eliminating repair capability. The psychological impact of rapid repair capability extended beyond immediate tactical advantages. According to intelligence reports, Japanese aircrew reports consistently overestimated damage effectiveness, leading enemy planners to believe that airfield attacks achieved longer-lasting disruption than actually occurred. American pilots observed that runways bombed at dawn were often operational by afternoon, creating confidence in forward-based security that enabled more aggressive tactical employment. The strategic impact of rapid airfield construction exceeded all pre-war estimates of Pacific campaign timelines. According to Joint Chiefs of Staff assessments from late 1943, Seabee capabilities compressed island-hopping schedules by 30 to 40%, enabling faster advances through Japanese defensive perimeters. Carrier task forces could withdraw earlier from contested areas, reducing exposure to land-based air attacks, while newly constructed airfields provided fighter cover for subsequent operations. Medium bomber ranges extended progressively across the Pacific as each new runway shortened flight distances to subsequent targets, creating overlapping zones of air superiority that gradually strangled Japanese supply lines. The economic implications provided significant strategic advantages that influenced resource allocation decisions throughout the Pacific theater. According to War Department cost analyses conducted in late 1943, Coral and PSP runways required 75% less shipping space than equivalent concrete installations, while providing 90% of operational capability for fighter and medium bomber operations. Material costs averaged $180,000 per runway for Coral and PSP construction compared to $2. $8 million for concrete installations, enabling construction of 15 airfields for the cost of 2 permanent installations. Labor requirements proved similarly advantageous, with Seabee construction requiring 2,400 man-hours per runway compared to 18,000 man-hours for concrete construction using traditional methods. The shipping efficiency gains proved particularly valuable in the logistics-constrained Pacific theater. According to Navy transportation analyses, PSP materials for one runway required only 3 LST loads compared to 45 LST loads for equivalent concrete materials. This efficiency enabled simultaneous construction of multiple airfields that created redundancy and operational flexibility previously impossible under conventional construction constraints. Construction timeline advantages compounded these savings, as rapid completion reduced security requirements and enabled earlier redeployment of combat units to subsequent operations. When combined with reduced vulnerability to enemy interdiction due to faster completion, the economic advantages of Seabee construction methods exceeded initial cost calculations by factors of 4 to 5. Construction costs breakdown revealed additional advantages in Pacific operations. According to Bureau of Yards and Docks accounting records, material costs represented only 40% of total runway expenses for Coral and PSP construction, compared to 75% for concrete installations. Labor efficiency gains resulted from standardized procedures, specialized equipment, and experienced crews that achieved higher daily production rates than conventional construction methods. Equipment utilization rates exceeded 85% due to simplified maintenance requirements and parts availability, while concrete installations typically achieved only 60% equipment availability under Pacific conditions. These efficiency gains enabled construction schedules that supported strategic timelines previously considered impossible for Pacific operations. Tactical innovations influenced broader military engineering doctrine. According to Army Corps of Engineers assessments, rapid runway repair techniques pioneered by Navy Construction Battalions proved superior to traditional methods emphasizing permanent reconstruction. The modular approach using prefabricated materials enabled faster damage recovery and reduced vulnerability to repeated attacks. These methods were subsequently adopted by Army engineer units operating in the European theatre, where airfield repair capabilities proved critical for supporting tactical air operations. Personnel costs remained remarkably low throughout the Pacific campaign, despite consistent operations in combat zones, where construction sites attracted concentrated enemy attention. According to Bureau of Medicine and Surgery records, construction battalions experienced casualty rates below 3%, despite operating in active combat zones where Japanese forces specifically targeted airfield construction as high-priority strategic objectives. Defensive training programs emphasize small unit tactics, perimeter security, and coordination with Marine and Army combat units that provided effective protection for construction sites during vulnerable phases of runway development. Rapid construction timelines minimized exposure periods in contested areas where enemy forces could organize sustained attacks against work sites. Medical support systems established by Seabees units provided additional strategic value through comprehensive healthcare services that supported broader military operations beyond immediate construction requirements. According to medical reports from multiple construction battalions, Seabees hospitals and aid stations treated an average of 2,400 patients per month, including combat casualties from Marine and Army units operating from newly constructed airbases, tropical disease cases requiring specialized treatment, and injury cases resulting from construction accidents and equipment operations. Medical capabilities included surgical facilities equipped for major operations, blood banks maintained through voluntary donor programs, laboratory services for disease diagnosis, and dental facilities providing routine and emergency care for military personnel throughout forward areas. The integration of medical services with construction operations provided unique advantages in Pacific theater logistics. Seabees medical units arrived with construction forces rather than following weeks later as separate deployments, ensuring immediate medical support for assault forces during critical initial phases of operations. Medical facilities were constructed using standardized designs that enabled rapid establishment and expansion based on tactical requirements, while medical supplies arrived on the same LSTs that delivered construction equipment and materials. This integration reduced overall logistics requirements while providing medical capability that exceeded standards for similar-sized military units operating in forward areas. Equipment losses proved manageable through careful maintenance procedures. According to Bureau of Yards and Docks logistics reports, machinery availability rates exceeded 85% throughout 1943 and 1944, despite harsh operating conditions. Standardized equipment sets enabled efficient parts supply and repair procedures, while operator training programs maintained high proficiency levels despite personnel rotation. The durability of American construction equipment under Pacific conditions validated pre-war procurement decisions and influenced post-war military engineering specifications. Japanese responses revealed the strategic significance of Seabees capabilities. According to intercepted communications analyzed through MAGIC, Japanese commanders repeatedly expressed frustration with their inability to prevent Allied runway construction or maintain effective interdiction of completed facilities. Air raids could crater runways temporarily, but repair capabilities ensured minimal operational disruption. Artillery bombardments proved ineffective beyond close range, while amphibious counterattacks arrived too late to prevent airfield completion. The cumulative effect fundamentally altered Pacific warfare dynamics. According to theater command assessments, each new airfield multiplied American offensive capabilities while reducing Japanese defensive options. Fighter cover extended progressively across the Pacific, protecting bomber formations and naval units operating at extreme ranges from major bases. Medium bomber squadrons could attack targets previously beyond operational reach, systematically destroying Japanese air strength and merchant shipping. As airfield networks expanded, Japanese forces found themselves increasingly isolated, unable to receive supplies or reinforcements adequate for sustained resistance. The rapid airfield construction techniques developed by Seabees establish principles that continue to influence modern military engineering doctrine. According to current U.S. Air Force Rapid Airfield Damage Repair (RADR) procedures, many techniques pioneered in the Pacific Theater remain standard practice for expeditionary operations. Modular surfacing systems evolved from PSP technology continue to provide rapid runway capability for forward-deployed aircraft. Pre-positioning of construction equipment and materials, first implemented by Seabees battalions, became standard doctrine for global basing strategies. Contemporary analysis reveals the sophisticated engineering principles underlying Seabees construction methods. According to modern soil mechanics studies, coral formations provided ideal characteristics for rapid runway development due to their natural gradation, drainage properties, and compaction behavior. The Seabees' empirical understanding of coral as construction material, developed through field experience during 1942-1943 operations, aligned closely with engineering principles not formally recognized until decades later. This practical knowledge enabled construction rates that exceeded theoretical calculations based on standard engineering procedures. The integration of construction and combat capabilities influenced broader military organizational concepts. According to current doctrine development, modern engineer units emphasize dual-role training, combining technical expertise with combat proficiency. This approach, first implemented systematically by Naval Construction Battalions, proved essential for operations in contested environments where construction sites required active defense. The concept of self-sufficient engineering units capable of independent operations became fundamental to expeditionary warfare doctrine. Logistical innovations provided templates for modern expeditionary construction. According to current military logistics doctrine, the practice of matching construction equipment to available transportation capabilities, pioneered during LST-based Pacific operations, remains essential for rapid deployment scenarios. Standardized equipment sets enable efficient maintenance and parts supply, while simplified procedures reduce training requirements and operational complexity. These principles proved particularly valuable during recent humanitarian assistance operations, where rapid infrastructure development under austere conditions paralleled many challenges faced by Seabees during World War II. The Naval Construction Battalions, created during World War II, demonstrated that American industrial methods could transform the fundamental dynamics of military campaigns through rapid infrastructure development. According to post-war strategic assessments, Seabees capabilities compressed Pacific campaign timelines and enabled operational concepts that would have been impossible using traditional construction methods. The 20-day 6,000-foot standard established by these units represented one of the earliest demonstrations that speed could substitute for elaborate defensive measures in contested territories. By completing airfields faster than enemy forces could organize effective countermeasures, Seabees effectively neutralized Japanese defensive strategies based on denying Allied air operations. Modern expeditionary engineering continues to reflect principles pioneered by Naval Construction Battalions during 1942 to 1945. Rapid damage repair, modular construction systems, and integrated logistics support trace their conceptual origins to techniques developed under combat conditions. The convergence of industrial capability, technical innovation, and tactical necessity that characterize Seabee operations provides a model for contemporary military engineering challenges requiring rapid infrastructure development. Current doctrine, emphasizing agile combat employment and forward operating base establishment, directly reflects strategic concepts validated through Seabee construction capabilities. The strategic equation that governed Pacific warfare from 1942 onward remains relevant to modern military planning. If engineering units can establish operational infrastructure faster than enemy forces can destroy it, air superiority becomes inevitable. Seabee Construction Battalions proved this principle through systematic application of American industrial methods to military engineering challenges, creating capabilities that exceeded all pre-war projections and fundamentally altered the trajectory of Pacific operations. Their legacy continues through current expeditionary engineering doctrine and rapid airfield damage repair procedures that trace direct lineage to techniques pioneered on coral atolls during World War II. This episode revealed how industrial construction methods could achieve strategic air superiority in 20 days rather than the 6 to 8 weeks anticipated by Japanese planners. Leave a like, subscribe, and share in the comments your thoughts about how Seabee engineering innovations continue to influence modern military construction doctrine and emergency response capabilities worldwide.